All right, thanks, Jan, and thanks to Stefan and you guys for having me here. It's really great to be presenting this with you all. As Jan mentioned, I'm one of the founders of Electrosmith. We've only been around for a couple years, but the big project that took over all of our time this year was the Daisy, which some of you may or may not be familiar with, but it's a really exciting new platform for us and for quite a bunch of other people that we've been talking to this year. And so I wanted to take this opportunity to present it in the modular context and program it in C++, which I will go over. So I made a video presentation that I will now play for you. Hello, everyone. We're going to walk through the process of creating a Car Plus Strong physical modeling voice. We're going to use the Daisy embedded platform inside of the Daisy Patch Eurorack module to accomplish this. So let's start with what is the Daisy. Daisy is an embedded platform specifically designed for music and audio applications. So we really wanted to address the specific needs that audio tends to have, which usually amounts to processor cycles, memory, and high fidelity audio in and out, specifically, or an audio codec in this particular case. And so we came up with this idea for the Daisy a couple years ago, worked on it quite a bit, and finally brought it to fruition February of this year, 2020, and we launched our Kickstarter, which did really well. The response to it was spectacular and was more than we even hoped for up front. So this shows you the Daisy right here. This is the brain of the platform, the Daisy seed. So this is the little dev board, kind of looks like a teensy, but it's a little longer. You have 2 rows of headers. These come installed on the Daisy when you get it. So normally there's male headers here on this 1x20 strip. And you can program it over USB. This is the processor here. It's a STM32H7 series processor. It's very fast. It runs up to 480 megahertz. This is our SD RAM. You have up to 64 megabytes of SD RAM available, external SD RAM, in addition to the internal RAM, and then the audio codec. And we're using a really quite nice AKM audio codec, which has 192 24-bit processing, and altogether it really equates to some nice audio that's easy to set up, easy to flash, and easy to program, we would hope. And speaking of programming, there's a lot of ways you can program the Daisy. It's compatible with, you can export from PD, pure data. You can use C or C++. You can almost use Max MSP which we're about to have ready very soon. And a few other integrations are in the works. But today we're going to be using C++ along with our specific libraries, the libdaisy and daisy-sp libraries, which we'll get to in a moment. So, like I said, this is the Daisy seed, but we're going to be using the Daisy patch, which looks like this. And it's essentially just a fancy breakout for the Daisy seed. So you'll notice the seed sticks through the front panel here so that you can get your USB cable in, press the user and boot reset buttons, and then it breaks out all of the signals from the Daisy seed to standard Eurorack level signals. And so you'll have bipolar CV inputs, some gate inputs. Your audio is going to be converted from line level up to 10 volts peak to peak. And a couple other neat features here, an OLED display, SD card, and then we actually added a secondary codec on board the patch so that it has quad inputs and outputs. So it's really quite a fancy Eurorack platform, and it shows the full extent of what the Daisy seed can do. And if you're interested at all in the circuits of the Daisy patch, you can find it on our GitHub repo. The hardware GitHub repo is hosted on Electrosmith's organization page, and it's completely open source, so you can see how to convert your seed signals to any other level that you would want to use in different formats. And you're not restricted to Eurorack. We have a guitar pedal, the pod, which is just a little kind of portable USB-powered solution, and then we have a little desktop synth, the Daisy Field. So you can check those out as well. For today, however, we're going to be programming the patch in C++. So let's go over the libraries that we're going to be using. First of all, we'll be using libdaisy. And this is essentially deals with the nitty-gritty of the chip itself. So it doesn't have anything to do with audio per se. Libdaisy is all about talking to the chip so that you don't have to deal with the extremely low-level aspects of it. So setting the GPIO high or low, talking to the audio codec, the SD RAM, MIDI, all of this is going to be encapsulated into the libdaisy library. For those of you familiar with STM32, you'll probably know about the HAL, which is the provided library from STMicro. And we're rewrapping a lot of HAL functions into libdaisy to make it easier for our particular user base to make sense of. A little more of the audio organization, having the MIDI and the audio codec stuff wrapped up in terms that you would generally see in the audio world. And so that's libdaisy. You can find it here on our GitHub, MIT license. So feel free to check out all the code, use it, reuse it, so on and so forth. Very, very permissive MIT license on all the code that we supply so far, barring a couple of our DSP modules, which we'll get to next. The Daisy SP library is our DSP library, as you notice with the capital DSP. So this is our anything to do with actual audio and synthesis and effects and things of that nature are in our Daisy SP library. And we kept them separate because we really wanted each of these libraries to be able to fulfill their specific purpose to the best of their ability. And we didn't want the Daisy SP library to be restricted to only the embedded environment. So we wanted Daisy SP to be able to be used on a PC for testing, maybe on the web, maybe in a VST, all over the place, anywhere it could be used. And that's why we separated the two libraries. And so Daisy SP, it's written in C++. If I didn't mention that about libdaisy, it's also C and C++ code. You can find the list of the modules on the repo, which is really easy if you go to our modules folder. So you'll see we have quite a few things spanning, basic synthesis blocks like an AD envelope, ADSR, all the way to biquad filters, bit crush, delay lines. So it really runs the gamut. Moog ladder, it's a ladder filter. A lot of really spectacular DSP code here that we have either created ourselves or ported from venerable programs like C-Sound or that we found on the web, things of that nature. Another fun thing to mention here is we do have our documentation available on the web. It's pretty easy to browse. You can see the list of classes, pick one that you wanted to use. It will tell you the available methods, gives you a description, goes into a little more detail here. So this is a really nice resource to have if you are using the Daisy SP library. The first step, if you were going to be receiving your Daisy for the first time, would be to head over to our Getting Started wiki page. You can find this from all of the product pages for the Daisy products have this link on them. It's also a nav item, I believe, on the Electrosmith website, but it is just our Daisy Wiki GitHub repo, and it will have all the resources necessary, tutorials, what have you, for doing various things with the Daisy. So the homepage is our default Getting Started. This particular page will walk you through how to download an example, flash it to your Daisy, or rather you'll flash it using the web programmer that we have, verify its function and make some sound. We're going to go a little bit deeper than that since we want to write our own code, and we're going to write the code, compile it, and then flash it. So the first step you would need to do is to set up your development environment for the Daisy specifically. Now, depending upon if you're on Windows or Mac OS X, this is going to be quite different, so it's a little bit beyond the scope of this particular video, but if you are interested, you can follow this wiki page. It's not particularly difficult. We're using open source tools for what we are achieving. If you're familiar with GitHub, it will be much easier, and a couple command line applications or a couple command line utilities that we're using for doing the compilation and flashing. Knowledge of those would be useful, but not necessarily required for getting going here. Our documentation should be pretty clear, and you can always access the Daisy forum or the Daisy Slack workspace if you have questions. in that regard. So you'd follow this and install your development environment, and you'd be able to test it by compiling the Blink program, and you would not receive any errors, and you would know that you're good to go. So we're going to assume for this case that you've already done that step, because I've already done that on my computer, and we're going to move on to the code section. So for today's video, we're going to be using VS Code. You could use any IDE you want for this, of course. You know, Sublime Text is a really popular solution. You could do Visual Studio if you're already familiar with that. VS Code is a new thing Microsoft came out with, which is like a slimmed down open source version of Visual Studio, which we're liking a lot, especially for people who are wondering which IDE to use for DAISY. It's a lot simpler than Visual Studio, which tends to be better for a lot of the use cases we're going to be dealing with here. And you can also access some debugging. We won't really go into that today, but you can find some helpful tips for that in our user base about setting up debugging with VS Code. So if you wanted to use this IDE, you could just go to code.visualstudio.com, and it's cross-platform, it's free, it's nice and easy, painless to install, really quick. If you've ever installed Visual Studio, this is the complete opposite experience. It's very easy and simple to get up and running with. So I already have mine installed, but you would be able to just go ahead and do that on your own. Next, if you set up your development environment, you would have cloned our DAISY examples GitHub repo. We can just check that out real quick. This is what houses all of the example programs for the DAISY, whichever hardware platform you're interested in. So when you're setting up your development toolchain, the way we usually teach that is to clone this with the submodules already for libdaisy and daisy-sp. You'll see those here. And then build the libraries and then start from there. And so we're assuming that we've already accomplished that. This is our DAISY examples repo here. We go into the patch folder. We'll see we have all of our DAISY patch example programs. Today we're going to be dealing with the pluck echo program. And so we would go here, and you can open this entire directory in VS Code, which would take you here. So then you can see, you can browse the make file, the CPP, and any other files that were in the directory. We are only interested in the CPP file, the C++ file. It is a single file example program. It's not too complicated, but there are some things. It's got a few different aspects to it. Primarily concerned with the fact that there is a display, there is the car strong synthesis, but there's also a delay line happening inside of the code, which adds a little bit of complexity to it, but it's really not too difficult, and we're going to walk through it line by line. So let's actually dig into a little sound demo of the pluck echo example program before looking at the code, so that when we're looking at it, we have an idea in our head of what it's going to sound like and how all the various pieces attach together. So let's pull up our DAISY patch here. So we have our DAISY patch. I've already flashed it with the pluck echo example program, but we will walk through that process as well once we're done examining and building the code ourselves. So I have the pluck echo loaded onto the DAISY seed, which is plugged into the DAISY patch, and it's in my Euro rack ready to go. So let's check out what that sounds like. If I press the encoder, it's going to trigger a note. And if I take a clock signal from the bloom and put it into gate in1, it's going to trigger it continuously. So here we have a nice low car plus strong note being triggered at a specific frequency. Our controls are all here. So control 1 is our coarse frequency. So you hear it changing the pitch. Control 2 is our decay time. So this is going to be the length of the note. And then controls 3 and 4 correspond to our echo, or our delay line that we have. Control 3 is the delay time. scrubbing effect there. And then control 4 is going to be our feedback. That's the example program. It's a very basic program. The control levels themselves are mapped to these little bars on the OLED, so you can see what they're set at quickly. And that's basically it. So let's check out the code now that we know what the end result is. So I'm just going to go top to bottom. And if you're familiar with C++, this should all be relatively straightforward. Even if not, I'd like to think that the code is still easy to understand in light of the fact that you understand what the instrument is in the end. So let's just dive right in. Right at the top, we have our includes. These are really straightforward. The daisypatch.h file really just offers a lot of easy functions, just utilities for dealing with the seed in the Eurorack world, rather than having to do these seed functions yourself, if that makes sense. So we can go ahead and take a look at the daisy patch file itself. What the daisy patch includes is the daisy seed, and then it just encapsulates a lot of utility functions mapped to the controls already, so you don't have to worry about which ADC input knob 1 is connected to, or which GPIO is controlling the OLED display, for example, things like that. So if you scroll through here, you'll see we have our daisy patch object. We have the start audio function, and you'll see things about the controls, update analog controls. So these are not seed functions because the seed doesn't have any analog controls by default, but the patch has a number of analog controls, which we would want to loop through at a specific frequency. And so we give a lot of just helper functions in the daisy patch, BSP we call it, board support. And so that's what that include is for. Let's go, lost ourselves. Here we go, pluck echo. Beneath that we have the DaisySP header file, which just gives us access to all of our DSP modules that we're going to be using. And then string, of course, is so that we can deal with character arrays and send them to the OLED easily. Beneath that, we have our namespaces. So if you use C++, this should be really simple. Daisy is our libdaisy namespace, and then DaisySP is our DaisySP namespace. This just helps prevent naming conflicts within our program, and so that we can access certain aspects of the libraries in a simpler syntax than we would have to do otherwise. These next defines are just simple macros to make the rest of our code a little more readable. Num voices is set to 32, so you can have up to 32 individual voices in this of this pluck instrument. So Daisy is really powerful. It can handle a lot of notes of polyphony. You'll come to find it's really capable of handling kind of these really larger than you'd ever need in the real world polyphony sizes. We don't really want to hear 32 notes of this pluck instrument, but it's nice to know that we could if we wanted to. Max delay, this is just setting the maximum time of our delay line. Our sample rate is 48K, so this is a 10-second max delay time that we're setting here. Okay, beneath that we have our daisy patch object called HW, which stands for hardware. So thanks to our daisy patch header file, we have a class called daisy patch, and we're going to create an object called HW, which is a daisy patch object. So this is going to be our little handler for talking to the patch hardware itself from within our code, and it will make our syntax nice and easy when we want to do things like access knob1, because we can do daisy patch.knob1, so on and so forth, and deal with our setters and getters through this daisy patch object. Beneath that, we are creating our polypluck object, which is a DaisySP module. And if you're not used to the syntax, this is a template. So it just allows code reusability. Basically in C++, it's a neat feature, which we use pretty sparingly. We don't use it all over the place, although I think this program does have two of them. Yeah, delay line is also a template. But you can read more on C++ templates if you want to dive into that, but suffice it to say it allows type agnostic creation and code reusability. So in this case, the polypluck, we can go to our definition there, And this is our Daisy SP module. This is the file for that. So we're creating a polyplug class. Inside, we're probably going to be creating some other pluck type modules to create the polypluck. I did not write this particular one. Looks like Stephen Hensley did. So let's just scroll down it and see where it's created. So at the very bottom, you'll see a pluck object being created. And so there's also a Daisy SP module called pluck, which is the core Strong implementation in our library. The polypluck just gives you a polyphonic version of that module, and it's sort of like a meta module. It just includes the pluck inside of it and makes it easier for you, the user, to create a polyphonic instrument without having to deal with all of the voice allocation aspects. If you were going to create the polypluck from scratch, you'd have to do all of this fancy active voice settings, so on and so forth from within your code. And that's the polypluck class. So we can go back to our pluck echo now. So you'll see we're just telling the polypluck how many voices we want, and we already defined our num voices up here to 32. So we're saying create a polypluck object called synth, and it's going to have a max polyphony of 32 voices. Below that is our delay line object, which is just a simple delay line. This is in our Daisy SP library as well. So you'll see, what did I do here?
Yeah, you're right. I was clicking the right thing, but it moves on now here. So
that is our polypluck object.
Yeah,
we created a polypluck object called synth, which has a max number of voices of 32 voices, which we already defined in our macro up here. Beneath that, we have our delay line, and so we're using a DSP object, Daisy SP object called delay line, and we're creating an object named delay. So if we wanted to look at the definition for this, we could go over here. Just a standard delay line. This is accessible from within Daisy SP. You can use it in a number of ways. Like I said, it's a template, so you can use different types of data for your audio buffer, which makes it a really handy thing all around. Beneath that, we have a reverb object, reverb SC. This was ported from C Sound, and that just gives us a little end-of-chain reverb that we're going to run the sound through, even though we don't have controls dedicated to the reverb specifically. And so at this point, we've included all the files that we need to, created some helpful macros, and created the objects that we need for the rest of our program to exist. And we make these objects live globally so that they exist in our main loop, but also inside of our callback. That's why these are global variables. And then beneath that, the one other variable that we need in both functions is the smooth time. And we'll get to this a little later, but it's essentially just a value we're going to run through a filter to smooth out the changes of the delay so you don't get a lot of zippers and crackles and pops and other audio artifacts that you would otherwise have happening. So let's skip the audio callback for now and go to where the program actually starts running, which is our main function. If you've done any Arduino programming, you'll realize you have your setup and your loop. And this is essentially the setup of our program. So as soon as the chip boots up, it's going to come into main. It's going to do all of our initializations. It's going to hit this for loop where it just loops forever. And that's when our callback is going to take over and start running. So right now, we're just going to handle all of our initializations and tell everything what we want it to be before the audio starts being generated. So let's just start at the top. Sample rate. This is going to be the sample rate that we set for our audio. Hardware.init. You'll recall this hardware is our Daisy patch object. and you can access the init method just through this simple syntax, hardware.init. And then let's actually take a look at that just so we can understand what's happening here. So the init method is going to handle all of the initialization for the daisy seed that we don't actually have to worry about, but we understand is necessary since we're in the patch environment. And so you'll see within the patch, it's going to configure the seed, it's going to set our block size, init the audio, the display. The display would not be on a pod, for example. CV outputs, the pod would also not have CV outputs, so on and so forth. MIDI, and all the way up down to a couple more screen things. And if you wanted to create your own URAC module using the daisy seed, the daisy patch class is a great place to start because you can take all of these functions and wrap them however you want according to your own hardware configuration. And that's what's in the hardware.init method. You don't have to worry about it too much, just call it and it's going to do what you want it to do. Make it really easy. Sample rate, there's two ways to deal with this. We're taking the default sample rate of our session, which is going to be 48 kilohertz. That's just what the seed's default is, and so we're okay with that. So what we're basically saying is, hey, return audio.sample rate, hardware.audio sample rate. It's going to say, okay, it's 48K, and we're going to assign that to sample rate. And then we can tell all of our other objects what the sample rate is. There are also methods that would allow you to set the sample rate. So you could set it to anything you wanted. Well, you can set it to what our library, the default options that we give you, which I think right now is, I can't remember exactly, but it's 8, 16, 32, 48, 96, something along those lines. But for now, we're just going to make it simple, and we're just going to say, whatever the default sample rate is, give me that, and I'm going to pass this value around where it needs to go. Beneath that, we have our display initialization. So we're going to create a string that just contains pluck echo. It's just the name of the program. We're going to format that, and then we're going to write to the display right during the init. And you'll notice when we flash our program, it's going to pop up and say pluck echo, and it's never going to say that again. And that's because we have that in our init function. This never gets called again. It just happens right when it starts running the first time. Hardware.display.update. This just causes whatever value you push to your display buffer to be updated on the screen. And then we create a little delay just to give the screen itself some time to compensate for that. Beneath that, we move on back to our synthesis. And so we're going to initialize our pluck echo object by calling the init function. And the only argument required for that is sample rate. So we pass in our sample rate, which we already got returned from our seed object, or via the patch. We got our sample rate. We're going to initialize the delay, which doesn't need the sample rate in its init function, but we are going to set the default delay time to our sample rate times 0.8, which equates to a half-second delay here. And then lastly, we have our reverb initializations. It needs to know the sample rate, and then you don't have to set these other things. It would just default to what it picked, but we have a couple of just default settings for the sound here. And we're not actually going to touch these because we don't have any controls mapped to our reverb as it is. Beneath that, we're going to start the ADC and the audio. And so the ADC here, just to be clear, is not actually referring to the audio analog to digital conversion. This is referring to the control analog to digital conversion. So the daisy seed itself has 16-bit ADC inputs for controls. So these are not something you're going to want to use for audio. They're not designed to be used for audio, but they are extremely high resolution control ADCs. So they're going to be read at a slower rate. You can read it at audio rate, but it's really designed to be, normally the typical rate here would be your control rate, which is usually once per sample period, but not at your sample rate. Or once at your callback rate, not at your sample rate, rather. And so we're saying start the ADCs, and so it's going to start reading all the values from our pots and our CVs and our gates. And then we're going to say start the audio, and we're going to tell it which function to use for our callback. So whatever function you tell it here, it's going to run that at the specified frequency. After that, we just create our basically just an endless while loop. It's a for loop, but it just runs forever and continues to continues to call the display controls function, which is why we see our controls mapped to the patch's OLED display. And display controls is a patch method. We don't have to write it ourselves. So it's a really useful thing for you to use in your own code if you want to just display the controls if you're debugging or if it's just useful. You can call the hardware.displayControls method, and it's going to handle all of that for you. That is the initialization section and our whole main function. Now let's check out the audio callback, which will be being called by the chip at a set frequency that we already set up in our init. So we'll go to the top here to the audio callback, which we already passed in as the name of the function that is going to be called. So if you're familiar with audio programming at all in C or C++, you've seen this. It's a really common format. You have your input buffer, output buffer. We're using floats because we have an FPU on board the chip, so we can do it with any processing penalties. And then this is just the size that we're going to be looping through of our buffer. So at the top, we have all of our local variables. These exist within inside of the callback, but they're going to be deallocated at the end of it. That's important to keep in mind. Beneath that, we have our buffers. These are just for readability for us to be easier to read the code and write to and from the input and output buffers, in this case, just the output. And then beneath that, we are going to handle our controls. And so this is an important thing to talk about here. We are going to do this at what would be considered sort of a standard control rate. So once every 48,000 samples, since this is our sample rate, once every 48,000 samples, we're going to update our controls.
So I wanted to pause briefly here and just mention that I misspoke. It's once per block, not once per 48,000 samples. So it's far more often than would be led to be believed by the misspeak there. So once per block size is the control rate.
Our pots, our CVs, our gates, so on and so forth. We don't want to update these at the audio rate because it would put a pretty severe strain on the CPU, and we don't need to. There may be a time when you need to put certain controls inside of the actual callback rate. This is not one of those times, so I won't really dig into that here. So suffice it to say that we're going to be doing that outside of the actual for loop, which generates our audio. So these are some very handy patch functions, debounce controls and update analog controls. The first one, debounce, if you're not familiar with that term, it is basically to eliminate any noise that will happen on switches when you're changing state. So if you go from high to low, there's going to be a few milliseconds where you could have some spurious on-off signals, and this just allows a settling period before reading that value. Beneath that, the update analog controls is going to loop through all of the patch controls that it already knows about because it knows about the DAISY patch, and it's going to process that ADC and return the value into the patches controls so that we can then access them later and assign them to our own variables as necessary. So that's going to handle all of that. Once we go beneath that, we can handle our triggering of the voice. There are two ways you can do that with this program, via the encoder. If you press the encoder, it will trigger a note, or the gate input. And so the encoder is a very simple syntax, hardware.encoder.rising edge. This will return true if it's currently sensing a rising edge, or the gate input is high. And so we can access the gate input via the hardware.gateInput, and then you need to tell it which gate input we're talking about. And so that is this particular part here, gate in 1.trig. This will return true. If trig is high, it's going to return true, and that would trigger this if statement to also trigger our local variable to be a 1. Beneath that, we are doing some scaling, reading and scaling for our frequency value. The poly pluck object itself wants its frequency set in MIDI notes. And so what we're going to do first is hardware.getControlValue, control 1. This is going to return the ADC value that was already read and return it. And then we're going to scale that value between our MIDI note range and assign it to NN for new note. That's what that stands for. And then we're just going to quantize it to semitones. That's what this cast is doing here. So we now have an NN variable which features our control 1 value mapped to a range that our DAISY object wants it in. Beneath that, we set up our decay value for the pluck object, and it's very similar. You should get used to this by now. Get control value, but we're going to set it to control 2, and then we're just going to scale it between the range that we want, and that's what these two numbers are, and then assign that back to our local decay variable. And then once we've done that, we can then assign it to our actual pluck object, synth.setDecay, and then we just pass in our decay variable. Beneath that, same exact thing, but we're going to do it for the delay. It's a little more complex. There's a little more math scaling here, just due to the nature of how we want to scale it, but we're getting our control 3 value, we're putting that in a decay val, and then we're doing some math here to scale that range to the delay time range that we actually want, and then we're doing the same thing for feedback, and then we're going to apply those lower into our actual delay, but we do that at the callback rate so that we can minimize audio artifacts. Now we have our synthesis section. So this is where we actually fill up the output audio buffer before passing it along through the audio codec. So it's just a for loop, which is going to loop through each sample according to your size, and then pass it into the output buffers. So first up, we have our delay. We're going to smooth out the delay time through a one-pole filter. That's what phone pole is. And then we're going to use that new filtered value and pass it into the set delay setter method on the delay object. The reason we do this in the audio callback is to reduce any zipper sounds or other artifacts that may occur if you ran it at the control rate, which is much slower. Beneath that, we're going to generate the actual plucked note, and to do that, we're going to call the process method, which returns one sample from a DaisySP object. They all have the same process method, and that just returns one sample, which you can store into a local variable. Beneath that, we have our delay line, which is a very similar thing. We're going to take our signal and multiply our wet delay signal times its feedback, add those together, and then pass that into delay.write, which is just a method for writing to our delay line. Beneath that, we have our reverb send. So we're going to do a very similar thing where we're going to add the dry and the wet together, scale them, and pass it into the reverb. And then last but not least, we just assign it to the actual output buffers themselves. So we're going to take our dry signal, add it to our wet signal, pass it into the left, and then do the same thing for the right. And at that point, our output buffers will be filled up at the sample rate and then dumped out to the audio codec in time to be sent out to the actual DAISY outputs. So that is the program in its entirety. It's relatively straightforward. Thanks to all of the abstraction, we have quite readable code, in my opinion. And it enables us to take a more musical approach to the code than it would be if we had to write all of this from scratch every time, which is the benefit of using the DaisySP and libdaisy libraries. So now, let's flash this program to our Daisy patch and take a musical listen to it. So for that, we will go to the Daisy web programmer. You can access this from our website, or if you know the URL, you can just grab it here. Now, what we need to do is put these Daisy seed into bootloader mode, and which means it's ready to accept firmware. We'll connect to it, flash the firmware, and we'll be good to go. It's important to note you need to use Chrome in order to use the web programmer. It's cross-platform, but it does need Chrome, and if you're on Windows, you may need to update your USB driver, which we also have a wiki page on. So what we're going to do is we're going to head over to our Daisy patch, and we're going to press the boot button. We're going to hold it down, and then we're going to press the reset button. Once you've pressed the reset, you can let go of boot, and it's now in bootloader mode. So when we hit the connect button here on our web programmer, you're going to see something called DFU in FS mode. This is the Daisy seed. So select that, hit connect, and now we're connected. So now we can select the firmware that we want to upload and flash it to the Daisy. So we're going to say patch for our platform and pluck echo for our example. Now all you need to do is hit program. It's going to give you a little progress bar, and it'll tell us once it's done. There we go, all done. And so that took place over the micro USB cable here, and we didn't need any intermediary hardware going between our computer and the dev board. One other thing to note, just our web programmer, we try and flush out each example's page with some useful information. So at the top, you'll see a little table of the controls, a little diagram showing you what corresponds to what, And sometimes we'll have a little video snippet down here, maybe a SoundCloud example. We don't have that for this one, but we do for a couple of the other ones. Okay. Now that we've flashed the code, let's take another listen and try and explore this in a little bit more of a musical context, maybe. All right, so we'll patch in our clock signal from the Bloom. There we go, our plucked voice. And let's now take our sequence signal out. So this is a vote per octave sequence. We'll plug it into control 1, which is our pitch. And you'll hear the pitch changing. So that's nice, get some delay. Let's now patch in some random voltage. We're going to grab it from the chance, which is out of screen, but we'll put that into our decay. So you'll notice our decay is changing. Now we'll take some more random voltage. We'll plug that into our delay time. And then we'll grab some smooth random voltage, plug that into our feedback. So this is just 3 modules, and you'll see we're getting quite a lot of results for the few things that we had to do here, because a lot of the DSP is just encapsulated in the DAISY patch, and we're able to take advantage of these a multitude of processing effects localized to a single module. Just apply some CV, some modulation, and we can get quite a wide range of sounds in the output. I hope that was helpful. Thanks for watching.
Thanks. Yeah, if there's any questions, I'd be happy to field them now. Should I stop presenting? But yeah, I'd be happy to answer any questions anybody has. Yeah, I would love to give some updates on that too. So I saw Stefan asked about the Gen export. So we have a lot of great news on that this week. Actually, we went into our internal beta on that, and so we've been flushing out just minor platform inconsistencies between Windows and Mac OS X. But we are expecting to do a smaller public beta next week on the Gen export, and so I know a lot of people have been waiting for that. That should be really exciting. And it really turned out pretty spectacular. There's a lot of unique features to the Gen export. You can load in a bunch of different patches at a time, all onto the same program. And so it's almost as if you're running like 10 programs at once onto the DAISY. And so keep an eye out for that next week. We should have some updates for that. And then as far as the Faust integration goes, one of the next big things on our roadmap that I think Faust is waiting on is getting code execution from our QuadSpy storage. One of the things about the DAISY is the particular processor has a smaller amount of internal flash memory, which is where you usually execute code from. This is what enables us to sell it at a nice price point. However, it makes it a little more difficult to load in large programs. So if you're writing little embedded modular or guitar pedal programs, no problem. But as soon as you want to integrate a larger, more sophisticated language like Faust, you're going to need a little more flash memory. And so we did put a 8 megabyte quad SPI chip on there, and then we can execute code from that chip. We just haven't added all the drivers to do so. But that is coming up in the next month or so on our roadmap, and then hopefully we can move forward working with Stefan on the Faust integration. Yeah.
Yes. So I can maybe comment. So we have now, do you hear me? Yes. We have received 2 different models. We have a pod action sent by you, Andrew, and your colleague, I guess. And we had also a guy just sending us a patch just because we are I don't know, he was a gift in some sense. And we need to expand our architecture file to be able to program any model, because right now it's not expressive enough to be able to do that. So I have to work on the other model. And the second point is, yes, the size of C++ that we export, but basically not exactly our code, but as soon as we use IO stream, for instance, it adds some a big bunch of code. So maybe either we have to remove some or rewrite some of our architecture file. So it may be a way to improve that. Or if, as you said, if you improve the situation or your side, it will be easier for other projects also. So maybe it makes sense.
Yeah, definitely. And just regarding to the model comment that you made, we're working on documenting each specific type of hardware with a JSON file. Because we have the patch, the pod, so on and so forth. So all of the controls are going to be mapped in a JSON file, which we're then going to try and use. And we've been doing this for Gen, where it kind of knows which controls to already map based on the board specification in the JSON.
So it means by reading the JSON, we could have a kind of generic system that would adapt to a given hardware. So maybe it's the way to go. Yes. Okay.
Right.
Okay. Nice. Yeah. In a more generic way. Otherwise, we have to tweak the code each time. So yes. One way to have, we were thinking at some point with a kind of CSS model when you could separate this kind of description in a kind of separated file, so that you could trying to avoid having this part of the connection done directly into the source code. So this is a way to think about. But now, since we have now a lot of people trying to use Faust into the embedded world domain, TeamZ, Space 32, Daisy, Bella, the problem Common Score and also old. So we have to find a generic solution, otherwise it is the time to try to find a better way to do. There is also another question that we have to solve. It's memory allocation issue. It's somewhat separated from the C++ code size. In Faust, right now, we just generate a flat memory region for the complete DSP, including delay lines. But obviously, at some point, this size is too much for the local memory, and you may have to decide that like the long delay line would have to be allocated at another place. And so to do that, we will probably one way to do that will be to give an option into the compiler to add a kind of memory allocator that you can change, so that the memory allocator would decide where to put each kind of memory. So this is something also that we have to think in a generic way, so that it would adapt to any kind of embedded device. Yes, yeah, because it's also the same issue with TINZ and so on.
Yeah, that's the first thing that everyone coming from a desktop programming background is confused about. They're always confused because they say, "Hey, I'm trying to do this thing with my buffers and whatever," and we have to tell them, "Hey, this is a different world than you're used to. You actually have to keep the memory aspect in mind because it's so limited. You don't have endless buffers and memory and RAM and everything." So it's definitely a shock for a lot of people. But
so maybe I have another question. We will start in a few months a project that will be sponsored by the National Research Agency here in France about using FPGAs. So what is your position as a hardware developer about FPGAs and ultra low latency and
So FPGAs are something we discussed a few years back. They're obviously, a spectacular solution to DSP hardware, and it really comes down to what your goals are in the end. For us, our choice of microcontroller was very specific because we needed it to be, one, an open platform, and B, we wanted to support as generic of a solution as possible so that you could add all the things you want. So what I'm talking about here is things like USB support, wireless connectivity, GPIO, things of that nature. So when you're looking at the audio hardware landscape, you're going to have a lot of options which have a lot of processing power, but the openness of their tools, the available free tool chains and flashing applications that you can use are not always available. So in that regard, things like the Shark processors, they're extremely powerful, but if you want to have all these other open aspects about it or allow people to have a lot of freedom, it's probably not the way to go because it requires a proprietary IDE, flashing set, things like that. FPGAs are a little similar in that regard, not necessarily that it's all closed, but it becomes a little more difficult to program, which makes it a little less flexible, which was why we ultimately decided for the DAISY to go the route of the STM32 series processors because people are so familiar with it. There's so many free tools available, and it just gives you all these things for free, like being able to flash firmware over the web through USB. We didn't have to do a whole lot of work to implement that, which was really a big selling point for us. So I know FPGAs are a spectacular solution for DSP. It really just depends about the other added benefits that come with the platform choice overall.
Are there any other questions?
And that brings up another good point too. I mean, there's another really popular chip some of you may be familiar with, the FV1 by Spin Semiconductor. It's a really popular chip. It's similar, it's a really great DSP chip, but you can only program it in assembly code. And so the flexibility and the programmable nature of the FV1 is one of the big drawbacks to it. So it's a great solution for a lot of problems, and a lot of people, they have no complaints. But if you can only program something in one specific way, it limits the range of uses and places that it's going to wind up being used. So it's a little similar.
Hey, thanks for the great presentation, Andrew. today, is it possible to run the code on a PC or Mac, like to test, to prototype before flashing the DAISY?
That's a great question. I'm glad you asked that. So it's not possible yet, but we are very close to implementing something like that. And we are actually working on potentially doing a VCV rack module, which will let you prototype DAISY designs in VCV rack, and then you can export it to your DAISY once you've ironed out all the kinks. So that's one way that should be available pretty soon. And of course, we're working on that because we use DAISY day in, day out for our other projects, for other products we're releasing. And so we'd like to be able to develop at a higher level before worrying about performance constraints or anything like that, and iron out whether or not it's a good instrument from a musical perspective before ironing out and working on bugs and low-level problems that we don't necessarily need to handle at that point in time.
Okay. Are there any other questions? So, Romain, how was the truffade? Is it Romain still here?
So Roland, yeah, that's a great question. We haven't actually had anybody ask that question yet. I'm kind of surprised. Yeah, I'm sure that we will be supporting that at some point in time, and we'll make some tutorials to do it. We've never done it ourselves, actually. So 480 has been enough for all the things we wanted to do. So I will, yeah, let me talk with Steven about that. We can see about making some examples on how to do that. But that's a great question.